Hello, everyone. My name is Angeliki Lapa. Today, we're going to talk about variable selection in modeling with supersaturated designs. This is joint work with Professors Christos Kokouvinos and Marilena Mitrouli. First of all, I would like to thank the organizing committee of DESSERT for this opportunity to be here. So, let's see the contents of the talk. First of all, we're going to say some things about supersaturated designs and the linear regression model, along with the cumulative sum control result, which is a very powerful tool of statistical process control. Next, we're going to talk about some variable selection methods like SIS method and SIS-PURSUIT method. We're going to present our experimental results along with some examples and finally the conclusions and the references. Supersaturated designs appeal greatly to both scientists and engineers. They are designs with P factors with n runs, where n is less than P. They first appeared in Sutter White, and since then there has been a huge research regarding the construction and the analysis of SSDs. A comprehensive review can be seen in a year review in 2014. The analysis relies upon the construction, the assumption of sparsity, where we can say that only few factors are significant. The main goal of the screening experiment is to correctly identify the active factors while the inactive ones will be discarded. During the screening experiments, we consider the null hypothesis as 0 versus the alternative hypothesis. SIS-PURSUIT method that we're going to see later more extensively is detects active factors via the Kusuma chart in SSDs, assuming normally distributed response. Constitutes of two stages, where in the first we apply a raw screening procedure using SIS method, and then we apply the Kusuma chart in order to identify the active features. During the evaluation of a proposed method, like this, we evaluate the following criteria. Type 1 error, which is the cost of declaring an inactive factor to be active, where we reject the null hypothesis, and type 2 error, which is the cost of declaring an active factor to be inactive. Both of them must be kept as low as possible. Furthermore, in SSDs, controlling type 2 error, along with keeping statistical power as high as possible, is more critical than controlling type 1 error. Let's see the linear regression model that is given in equation 1, where y is our response vector, x is the design matrix, and beta is the vector of unknown coefficients, and epsilon is the random vector, assuming normality. Our goal in the screening experiments is to identify the non-zero effects, assuming there are up to m active factors from the total P involved. This is very important during screening experiments. First of all, let's see the cumulative sum control charts, which is a very powerful tool, as we already said, in SPC, statistical process control, and that will first appear by Page in 1945, 54, sorry, and where it's important because it detects very small shifts in the process parameters. For example, this chart is used for individual observations, and when the process is in control, we say that xi follows normal distribution with mi-zero mean and sigma standard deviation. The upper and lower Kusum statistics are given by equations 2 and 3, and C0 plus and C0 minus are the starting values that we used these cases for later during the SIS-PURSUIT method. K is the reference value, and we say that if Ci plus or Ci minus is greater than H with the decision interval, then the process is out of control. Note that both the decision interval and the reference value depends on H and K lower cases. These values are very important in the PURSUIT track because they provide a chart with a good performance. For more information about the choice of these values, we refer to Montgomery. Let's talk first about Sur-independent screening, which was proposed by Fanelli in 2008. It's a raw screening procedure that uses the property of Sur screening. It's a variable screening procedure which selects the important effects with probability tending to 1. What this method does, It takes a sparse model, and with descending ordering through marginal correlation, produces a submodel where it produces a smaller model with size d, which is less than n. This method, we used it along with Kusum chart in order in 2018 in Rosso et al. And proposed cis-Kusum method. This method, as we already said, is combined with the previous cis procedure, and we test the factorial effects in supersaturated designs. It's described as follows. Using X, which is the SSD matrix, and Y is the normally distributed response, we compute the least squares estimators using the cis method from 1 to m, where m is less than p. And this can happen because m is less than n, since we choose active factor up to the half of the range. Then we calculate the absolute effects of beta I, and using the absolute effects, we can calculate then the upper statistic CI plus. In order to calculate CI CI plus statistic of the Kusum chart, first we set the standard deviation of the effects equal to the square root of the standard error of the linear model that we already know it. And then using KH according to Montgomery, we calculate the decision interval and the reference value. Given all these parameters, we say that if the CI plus statistic is greater than 8, then we can say that this factor is important active one. Otherwise, we can say that this factor is inactive, and we can further investigate the other factors. Note that we only use the upper statistics since we use only the absolute estimates of the during this procedure, since the CI minus statistics of the Kusum chart will always be equal to 0. Furthermore, we use the starting value different from 0 because according to our simulations, we have better results. According to these simulations and in respect to type errors, we show that the formula given equation 4 produces better results, where you can see it depends on the number of runs, the number of predictors, and the number of active factors. During our simulations, we use several SSDs, supersaturated designs, with different sizes, proposed by Kubinos et al., Marley Woods, and Tankevaux. We compared the several variable selection procedures are cis-Kusum, cis, standard stepwise variable selection, and dancing selector that proposed by Foa et al. During our simulation procedure, we performed 1,000 simulations for each model, where the response was generated according to the linear model, and the SSD was the design matrix, and the error were normally distributed with 0 mean and unit variance. The number of active factors were ranged from 1 to the 1/2 of the runs, and the beta coefficients were generated from normal distribution for the active ones, and the inactive ones were set equal to 0. The Kusum parameters were set K according to Montgomery to K equals to 1.5 and H to 1.61. And during this procedure, we calculated type 1, type 2, as well as statistical power. According to our results, cis-Kusum improves the performance of cis. It keeps type 2 errors as low as cis. It reduces type 2 error up to 20%. And furthermore, comparing cis-Kusum with stepwise regression NDS, we can see that produces low type 1 and type 2 errors up to 1/3 of the runs. The type 1 errors of cis-Kusum for all the considered modes is lower than 10%. Type 2 errors are lower than type 1 errors for active factors up to 1/2 of the runs. And as for statistical power, cis-Kusum produces better results compared to the other methods and for all the considered models that we used. Next, we present the first example in our talk, where it's about the production of immediate release ciprofloxacin tablets, and it was presented in McGrath et al. In 2023. The design that we see in our slide, it's about 12 runs, is the rows, and 11 factors that were studied, and multiple response variables were analyzed: Y1, Y2, Y3, and Y4, as you can see in that slide. McGrath et al., as well as we considered two procedures. During one stage procedure, we selected the terms in the model all at once. First, we assume that we have all main effects and two-factor interactions. So we have 11 main effects that presented in the previous slide, along with the two-factor interactions, which were 55. And during two-stage procedure, first, we selected only the main effects that were important, and then all two-factor interactions that made the weak or the strong heredity added to the model, and then we selected the final model. Note that when we say weak heredity, we mean that if the model includes A-B interaction, at least one of A or B factors is selected, also included in the model. If we say that we have strong heredity, it means that if the model includes A and B interaction, it includes A and B as well. McGrath et al. Performed during one-stage procedure SCAD-C, thus SCAD along with CI criteria, and during two-stage procedures, they performed SCAD-C, ball correlation based Cs, and length test along with SCAD-C. During the one-stage procedure, we performed Cs, while in two-stage procedure, we performed Cs consumed twice. McGrath et al. And we performed our methods individually for each Y. So, for example, during the first Y1, we see that performance cut C in one-stage procedure, McGrath et al. Found that F is an active factor. It's an active factor. Cis consumed shows that F and IK are active ones, while during two-stage procedure, we can see that performance cut C twice, D and F are active. B correlation along with SCAD-C shows that DEF, AE, BF, and EF are actives. Performing length along with SCAD-C shows that D and F are active ones, and performing Cs consumed twice, we see that DF and DF interaction are active as well. In the next example that was presented in Grosso et al. As well, we consider a very well-known dataset in SSD analysis, where it's a William Rubber dataset, which proposed by Williams in 1968, where we have 14 runs and 24 factors. Note that the 13 factor and the 16 factor are identical, so one of them was deleted. So we have 23 factors. And the last column is the response vector. Performing the cis-consume method, here we can see the chart consume that was presented in this slide was the chart that we constructed. We can see that the 14 and 16 factors are important in our experiment, and this is very important and significant because other methods as well show that the 14 and 16 factors are important as well. Finally, we can say that SSD analysis is a challenging area of research. Especially cis-consume is a very important method because it keeps type 1 and type 2 errors as low as possible. The statistical power comparing to the previous existing methods produces very good results. And according to the real data examples that we saw, we can say that we can recommend it for variable selection and modeling SSDs. Finally, a serial procedure using consume can be performed assuming binary distributed response, and we can say that the further research can be done in multiple response analysis. Thank you.
Thank you.